liquid cooling is the most effective, and single-phase immersion cooling and direct-to-chip cooling are two leading technologies for implementing it. Compute density, total cost of ownership, and sustainability are key factors to consider when comparing these solutions. Let's explore how each technology works to make an informed decision. IT hardware generates heat that must be removed for optimal performance, with the heat transfer process differing by cooling technology. The first stage is transferring heat from the server to the cooling fluid. As your IT hardware powers up, the chip, typically a CPU or a GPU, is the primary heat source. With direct liquid cooling, a cold plate is typically attached to the primary heat source, the chip. However, components like memory modules still generate heat and depend entirely on air cooling. Adding more chips means more cold plates and tubing are needed too, increasing complexity as the server equips more of them. In this scenario, only 70% of the heat is transferred to the liquid. The remaining 30% must be handled by server fans, which extract heat using air. In immersion cooling, there is no need for fans. The server is fully submerged in a cooling fluid, which absorbs 100% of the heat generated by all the components. The first heat transfer stage has now been completed, with single-phase immersion cooling showing a clear advantage. It simplifies the server design, with a single body of fluid absorbing all the heat. Now, let's examine the second stage. Here, the heat moves from the primary fluid to a secondary one, usually water. A vast number of chips and servers are needed, and they are usually grouped in racks. In the case of immersion cooling, they are clustered in pods. In DLC, server pipes connect to a manifold, which links to a cooling distribution unit with a heat exchanger. Here, 70% of the heat moves from the primary fluid to the secondary fluid. However, the system's complexity increases due to the many pipes and connections, potentially affecting reliability. The remaining 30% of the heat still requires air to be removed, handled by a large traditional air cooling system. In immersion cooling, the hot immersion fluid is transported directly to the heat exchanger in the CDU, where it transfers 98% of the heat to the secondary fluid. The remaining 2%, originating from the ports and piping, is effectively managed by simple air handling units. At the second heat transfer stage, the simplicity of immersion is clearly visible. Moreover, it offers the advantage of concentrating the majority of the heat into one body of fluid. Simplicity brings reliability. In the final stage, the secondary fluid releases the accumulated energy via the heat rejection infrastructure. Usually, there are so many chips and servers needed that racks and pods are deployed by hundreds. Components like network switches may need air cooling, but are excluded here. With DLC, the portion of the heat handled by the secondary fluid requires a relatively small heat rejection system. In contrast, the portion handled by air cooling needs large air handles and heat rejection systems due to the lower thermal performance of the air compared to a liquid. For immersion cooling, the heat rejection system for the secondary fluid is relatively larger. However, the infrastructure related to air cooling is significantly smaller thanks to the very little capacity needed. At this point, the heat originated in the chip and other components has been released. While both technologies have a similar footprint, immersion cooling is far more efficient as it captures nearly all available heat. Though not discussed here, this makes immersion cooling ideal for heat harvesting and reuse. Direct-to-chip cooling uses a traditional rack form factor, but it carries vendor lock-in risks and increasing complexity. In contrast, immersion adopts a different form factor, is vendor-independent, and allows for flexible facility requirements. Operation of DLC is more similar to air cooling, but comes at the expense of higher critical failure impact. Immersion requires some procedural adjustments, but it is quieter and dust-free. DLC is slower to deploy and incurs additional cooling costs, with each IT refresh, whereas immersion cooling is more efficient and provides long-term viability. In conclusion, both DLC and immersion cooling deliver comparable performance regarding power density and space requirements. However, single-phase immersion cooling stands out with lower operational costs, adaptability to evolving IT demands, and best resource efficiency. Immersion emerges as the long-term viable solution for computing workloads, and here is where I thrive today. Want to dive deeper into the results of this analysis and learn more about liquid cooling? Contact Submer to gain valuable insight to help you achieve your goals. Submer, data centers that make sense.